Okay, welcome back again. So now we are changing topic in this session number 3. We will send you the slides. Doesn't need to make pictures, so send him the slides. The slides are available. Okay, so basically, I'm going to talk about photonic chip sensors, biosensors. Okay, so this is the contents of the presentation. As before, I will skip some parts, not to take a very long time. And I'm going to describe a little bit of the applications. Then I'll review some basic concepts. These presentations are self-contained, so maybe some of this, what is photonics and those things you already know, of course. I will review some terms and definitions that I need later on to explain you some of the on-chip sensing architectures and the applications, okay, and real-life applications. So, diagnosis today and tomorrow. Most of these slides are courtesy of a colleague, Professor Laura Lechuga, from the Catalan Institute of Nanotechnology in Barcelona. So, if you are interested, I have her contact, of course, and she has a lot of papers and projects that you can read about. Okay. So, basically, today, all analyses are done in analytical laboratories, which are centralized. Basically, they are centralized. They are run by trained personnel. Mainly, maybe in some cases medical doctors, nurses, or health assistants, and they are time consuming because it requires a lot of manual operations with substances, concentrations, etc. etc. Okay? They rely on expensive instrumentation, and since all of those, they are not available to everyone, so this resource is somehow constrained. Ideally, one would like to transition from this to a benchtop instrument, even to something even more simple, more handy for the point of care. That means that you can do the diagnosis out of lab, in situ, maybe in your local medical center, without needing to move to another city, to a big hospital to do a test. It should be fast. These procedures sometimes they take days because you need maybe there is not enough of what you are trying to detect for this instrument, so actually you need to grow it somehow, to leave it in temperature and humidity and grow it for some time, and in that time maybe the patient is so ill that they will already die, even if you know what he exactly has. It's too late, right? So it needs to be fast, it needs to be level free. Later on I will mention what is level free, and it needs to have high sensitivity. That means to detect with the minimum amount of substances as possible, with the minimum extraction from the patient as possible. Okay? And of course another thing important, if it has to be maybe even in your pharmacy, it needs to be user friendly and have an attended operation. It does not require a medical doctor to operate it. It could be operated by you and me. Okay? So, basically, sample, final diagnosis goal, and that means, okay, you have something. This is not like, okay, prescription. No. This is something, okay, maybe you should go to see a doctor, okay? But it is fast and reliable, okay? So, applications, it may have applications in bio, in chemical, and safety and security. For instance, in bio, to detect glucose, cancer, to scan your tissues, detect some proteins, DNA analysis, etc. In safety and security, because you can detect gases, hazardous substances, etc. And also in the chemical field, because you can analyze the composition of different chemicals in your sample. Okay. Then this brings me, or I bring back one of the slides that I showed yesterday several times, and I will show it today several times as well, where I just draw the optical spectrum with wavelength and wave number here. Physicists, you are also familiar to wave number more than me. And wavelength is related to the material systems that you can use to make photonic integrated circuits. These are material systems that you can use for photonic integrated circuits. And typically, wavelength is strongly related to the application. Biophotonics is done in between 400 nanometers up to 1000 nanometers, more or less. Okay? From 0.4 microns up to 1.0 microns in wavelength. Telecom datacom we've seen in the previous session, and next session we'll see mid-infrared photonics. So now we are concentrating on applications that are typically done with visible wavelengths. As I said yesterday, bio and tissues are not harmed by visible wavelengths, and that's mainly why visible wavelengths are used. Okay, and there are technologies to make chips on visible wavelengths. We'll see them later. Okay, so I'll skip this thing. As I said, this is like a general talk of what is a sensor, what is photonics, the properties of a wave, maybe for the less physicist trained in the room. Well, waves have amplitude, have phase, have intensity. So all these magnitudes can be used for sensing. Okay, it is interesting. It is interesting to know that in most of the sensors, the most sensitive things attained are by interferometry, and that means the phase of the light. Okay, this we've seen it in the previous talks how the phase is important. For instance, in a coherent link where you have phase modulation and a coherent modulator. In sensors, it is not different. Phase is really the important magnitude. And how you translate this phase into amplitude, which is easily measurable with a single photodetector, that is the truth. Okay? A photonic integrated circuit, I hope that most of you already know what is. For those that have just entered the room, a photonic integrated circuit is sort of a chip that guides light inside, and you can manipulate the light inside of the chip. Okay? Okay, so now a brief historical recapitulation on when the first photonic biosensors, or sensors as we know them today, appeared. I just did a search on Google Scholar and Scopus, which are research databases for integrated optic sensors. So in the 60s it was like, imaging sensors, and in the 70s, for instance, for gyros, and then now in the 80s, chemical and gas sensors references start to appear as we know them today. And it is the very first one was by accident, as most of the things that's happening in research and discovery, like the laser, for instance, it was by accident. So actually, this research group was researching on optics. And they had waveguides and they had grating couplers. I don't know if some of you are not familiar with grating couplers. So basically, if you have an optical waveguide and the light is contained in your waveguide, okay, the light is contained in your waveguide and travels that direction. If you make a corrugation of your waveguide here, when light reaches this area, it's scattered out in a given direction. Okay? So light goes in the chip and goes out of the chip. Okay? Well, these guys were experimenting with the chip, and this direction depends on these groups, on the refractive index here, on the refractive index here, and on the refractive index here, right? And these guys were like, close to the chip, touching the chip, exhaling onto the chip, and they realized that the power meter was giving power variations. Okay? And this was because they were changing the humidity around the chip, and they were changing the refractive index because of exhaling. They said, okay, this is a sensor. Okay, so this is the first type of sensor that was discovered, as I said, by accident. Okay, later on, more complex sensor, comparatively more advanced sensors with Mach cylinders were developed. So, but the first sensor in a photonic chip was a grating coupler, and it was by accident. Okay, so that was the introduction. Is there any question? Something that I said which is totally strange for someone?
Что означает PIC?
What's PIC? Where is that?
Photonic integrated circuit. Okay. Any other question? Okay, now I'm going to define some things that are required to understand the functioning of the sensor and which things are measured. Okay, so first of all, you just can shut your eyes, the guys that know what a waveguide is. And for the newcomers, a waveguide is some sort of light conduit. You can put light on it and it travels from one side to the other. Okay? That is an optical waveguide. And as I said, it's done on a chip. Okay, similar to the chips that you had inside of your cell phone, but with other materials and other dimensions. Okay, but you can guide light as well as you can guide electrons on a copper wire. You can guide light on dielectric or semiconductor materials. Okay, so the curious thing of this light is when you use the Maxwell equations to solve the electromagnetic distribution in this waveguide, you find that not all the light is contained in what you think is the actual pipeline of the light. Okay? Most of the light is inside, but some of the light travels outside. It is not lost. Well, it is lost when it's scattered, right? But ideally, it is there. It is outside. That means that if there is something outside, light can feel it. Okay? If you put something close, then you are altering the properties of light. And this is how the photonic biosensor works. This is actually called evanescent field or evanescent wave sensor. Because here you have a maximum of light, and when I draw it this way, it was not accidental. Here you have a maximum and then decreasing amount of light, but there is light outside the waveguide core. Okay? There is also another property of electromagnetism, for you that are not familiar, which is polarization of light, which is the orientation of the oscillation of this electromagnetic field. It is TE or it is TM. Okay? And in most of the cases, the waveguides can support both types of oscillations, TE polarization and TM polarization. And the beauty of this for sensors is that the field distribution of TE and TM is different. And you can see it in the picture. This is TE, transversal electric, and transversal magnetic. There is more light in the transversal magnetic outside for this particular waveguide than for the TE. Okay? So keep in mind, we are going to use waveguides in these biophotonic sensors, and we are going to take a profit of the fact that part of the light is outside the waveguide. Okay, so we still can guide it. We can do two things at the same time: guide and feel. Okay, guide and feel. Okay, and what can we feel? If we put something on top, this is similar to this representation, a 2D representation. We have our waveguide with a refractive index, a substrate, whatever, on top of which we build our waveguide. And here we can have air, or we can have a sample. Okay, a sample that we want to detect, to determine what is that, or how much of that do I have on top of my waveguide, basically. Okay? Then this sample is, whatever it is, it also has a refractive index. It also has a refractive index. Okay? And the propagation properties of this wave here depend on all the refractive indexes involved, not only the ones on the waveguide, but also the one on the sample. And it can either change the phase through the real part of the refractive index, or it can either absorb light. So you can see changes in phase, and you can see changes in the amplitude with a regular waveguide. Okay? I'll keep this one, and this one, and this one, and then I'll go to this. How is this quantified? Okay? I have a sample on top of my waveguide. How it is quantified? Which magnitude tells me the change? The change of what? Well, actually, there is a convention which is called refractive index unit. It is how much has changed the refractive index in the cover. Okay? So it is called, for instance, if there is an increment of the refractive index in the cover of 0.001, this is also referred as to 0.001 refractive index units, RIU. Okay? RIU, if you want to abbreviate. Okay? And I am advancing a little bit. You can see a picture here. What is this? For the optics guys. Can you tell me? What is this? Optics guys should tell me what is this. Looks like what photonic device is that? Sorry? An unbalanced Mach-Zehnder interferometer, right? Light is injected here, split in two parts, and then combined again. Okay? Keep it in mind. Mach-Zehnder interferometer is going to be important. Okay? I'm going to skip these ones, but I'm going to talk about another thing, which is the limit of detection. And to do so, I like to, because this is done with a special sensor, which is a ring resonator, that I'll explain later in depth, but I will recall it for those that have been with me these days and in October, and for those that have not been, please pay a little bit of attention. So this is a ring resonator. Light goes inside here, it makes round trips, and it goes outside, okay? And if you look at the spectrum response of this, it is like this, okay? But if you change something on the ring, this moves. So a ring can also be a sensor, okay? If you change the temperature, this peak will move. If you put something on top of it, it will change the refractive index, this thing will move. So actually, if you are scanning with a tunable laser and determining the position of this, if you see this moving, you can tell how much of something happened here at the top, okay? And this is what was done in this, I don't know, MRR for micro ring resonator for cytokine detection, okay? It is done with a ring resonator, and you put your substance on top. We'll talk about that later, it's not that easy. And basically, which is the minimum amount of analyte? Analyte is the substance on top, what you are trying to sense, analyte, which is the minimum amount of analyte that you can detect, okay? And the minimum amount that you can detect is called LOD, limit of detection, okay? This is the minimum amount. And all the sensors are always competing to achieve the minimum LOD, okay? Well, the minimum LOD is something that does not only depend on your sensor, and that is a pretty important concept I'm trying to convey. It does not only depend on your sensor, it does depend as well on your readout system, on how you put the signals in and how you read them out. In this case, I am talking about a tunable laser, okay? And the lasers, tunable lasers, do not tune continuously, they tune in small steps. The smallest step that you can tune fixes your limit of detection. In this case, a typical smallest step in a tunable laser is 1 picometer of wavelength. Minimum step is 1 picometer. And if you correlate 1 picometer to the substance concentration that you know when you calibrate the sensor, in this case is 1 nanogram per milliliter. Okay? 1 nanogram of the cytokine in a milliliter of maybe TDS. Okay? So two concepts that are made. Okay? Refractive index units. These refractive index units translate into a change that you try to measure, in this case in wavelength. And since your measurement system has a minimum resolution, that minimum resolution is related to the sensor limit of detection. Okay? Any question on this?
I have questions.
Okay, please.
We are working with the ring resonator. We are trying to test it like biosensor, but problem is that ring resonator depends on everything.
Yes.
Temperature and
Yes.
concentration.
Yes.
And something like that. For example, the quality of water.
Yes. Yes. The question is, are you willing to translate the question or?
You will translate.
No. I was going to repeat it in English, but maybe next time.
Проблема заключается в том, что эффективность плавления кольца и этого кольцевого резонатора может меняться не только от изменения концентрации конденсатного вещества, но от изменения любого фактора. То есть, если на этом кольце находится какая-то жидкость с большим количеством составляющих, то мы не можем сказать, какое конкретное вещество там изменяется, температура вещества изменяется. Что это такая ситуация?
Yes, that's a good question. Typically, what one does is, to use these structures as a sensor, you need a reference. Okay? And then what typically one does is to use two rings, for instance. Okay? And you send half of the power to one ring and half of the power to the other. And chemically, and that's important, you activate this ring to capture what you want to sense, and this ring you don't activate it. That means here you will be recording everything else, temperature, whatever, and here you will be recording temperature, whatever, plus what you want to sense. And by comparing, you can eliminate the unwanted effects and then keep the wanted thing. Okay?
That's only for temperature. What about complex liquids?
No. To detect things in complex liquids, you need to use chemistry. I mean, this thing by itself does nothing without chemistry. Okay? I'm going to talk about photonics most of the time, but the professor that provided most of this material is an expert in chemistry and uses photonics in a basic way. Okay? The important thing here is chemistry. How you activate your sensor to only capture what you want. Okay? That is important. So photonics here is accessory. Okay? It's a means to do something, but the main thing is chemistry. Okay, then a distinction between labeled and label-free sensor. Okay, labeled and label-free sensor. For instance, you can see here two drawings. There is light going through this waveguide. There will be light going through this waveguide, and the target molecule that you want to sense is this. Okay, the yellow one. You have functionalized. The word is to functionalize, to make functional your waveguide in such a way that you can collect these molecules with these activated other molecules, okay? Proteins binding to something, okay? If you sense them directly, that is a label-free sensor, okay? Actually, you are sensing directly the unmodified analyte that you want to sense. If you need to attach something to your yellow molecule to sense that something, that is a label. Okay, so that is the case, for instance, in some magnetic inspection or visual inspection, where they inject you some liquids that when they are illuminated, for instance, with some X-rays or whatever, they are fluorescent. Those are labeled. Okay, and unlabeled is on the contrary. Without doing anything, you can see directly what's happening. Okay, so label-free, and ideally you want it label-free because labels also alter the properties of what you're trying to sense. So, and also it's another additional step. So more complex and maybe with additional difficulties. And to probe, I mean, this is how to sense, but then you need something that is called transduction. Is to translate that change in the photonic layer to something that you can read. Okay? And the transduction that I'm going to describe in all this lecture is change of refractive index. How the addition of this molecule here that changes the refractive index and changes the propagation mode is translated into, is transduced into a measurable quantity. So, despite I have also described it a little bit in the previous slide, and that is related to Juliana's question. I want to introduce the concept of functionalization. Functionalization is making your sensor active. Okay? Basically, it requires several steps. First of all, it requires preparing your sensor to receive the binding molecules, not the target molecules, but the molecules that will help you bind to the target molecules. Okay? So basically, absorption, covalent binding of the biomolecule to the surface, and then all the treatments necessary to preserve those molecules in the right orientation, in the right number. We'll see something later on. This is a FET sensor, a field effect transistor sensor, source, drain, and with some functionalized biophotonics. Okay. Yes.
Вот у этих чувствительных меток есть чувствительность к веществам определенным или неважно какое вещество просто? Есть ли селективность, да, вот этих меток?
Я думаю, что здесь больше белый вопрос, что каждое вещество чувствительно.
Есть метка, или она чувствительна ко всем, допустим?
Сам кольцевой структура, она чувствительна ко всему, ничего не говорит.
Ну, тут именно.
будет существовать уже теперь до времени.
Каждый метр, что определенную ситуацию.
Ну, that was a question that if you will functionalize the surface, for example, it will be sensitive only for one something or for several.
That's a very good question. That you can make selective functionalization. So actually you can functionalize one area to sense something, other area to sense other thing. And that is called multiplex sensing. So actually with the same chip you can sense several things. That comes later, but it's a very good question. Okay, so let me talk now about a little bit. I described the fundamental photonics physics below, and now let me talk a little bit outside the photonics and tell you what else do you need. Okay, this is, for instance, your photonic chip where you will put your light in and out, and you will functionalize some part of it. Okay, but you need also a light interrogation system. Basically, something that puts light in and out. Also, you have your photonic transducer, electronic control system, and of course you need something else which is microfluidics. Okay, microfluidics or microtubes to drive gases close to the vicinity of the waveguide. Okay, so not only with the chip only you are of course not, it is not possible to do anything, you need all these other ingredients. Okay, and you can see an artist's representation of all these. This would be the photonic chip. This will be the photonic chip with some cladding, and you can see here that there is some space removed on the cladding. Okay, so these are holes on the cladding of the chip. Later on we'll see another artistic representation. And on top of that you have a fluidic chamber, and on top of the fluidic chamber you have some pipes and tubes for the microfluidics to flow on top of the chip. And then you have the optical fibers to make light in and out of the chip. Okay, so basically you flow your substances through the chip and you inject light through the substances. Okay, so how do we do that? For instance, in a technology that we develop in Spain, in Barcelona, in the National Center for Microelectronics, using silicon nitride. I mentioned silicon nitride before. This is a technology, a photonic integration technology that allows the propagation of visible wavelengths. Okay, so we have a silicon dioxide substrate. This is not writing here, silicon dioxide substrate, and we define an optical waveguide on silicon nitride material. We cover it with silicon dioxide, and on some areas we selectively etch away the silicon oxide. Okay, this is related to the question before about referencing. On some areas you don't etch the silicon oxide. On some areas you etch the silicon oxide. So this is covered and not exposed to the analyte. This is uncovered and exposed to the analyte. Okay? And then, of course, you inject light, and you need the fluidic system on top to make it flow. Okay? I'll skip this one and go to this one. Questions up to this point? Am I going too fast, or everything is clear?
Looks like everything's clear.
Fantastic. Okay, so now imagine that you have a little bit more illustration on how this works. Okay, how this works. Imagine that you have a photonic chip with the sample flow and a device which has some wavelength dependency. Okay, wavelength dependency. Okay, like the ring resonator. So you need a tunable laser. You need a tunable laser. You need to make the light go into the chip, out from the chip, and to measure and to capture the power, the optical power that comes out from the chip. And this tunable laser, you scan the wavelength. Okay, you scan the wavelength, and you get this. Okay, you get this. This is the typical response of a ring resonator. What happens if you put something on the chip? And what happens not only on a given time, but the evolution in time. It is important for most of the analysis also to see which is the evolution in time. Okay? So, at the very beginning, you see nothing because you're starting to flow the substance. So at the very beginning, maybe there is the background substance only, but when you combine it with your target substance, you see a wavelength change, okay? There is no wavelength change in this interval, so wavelength is here, but when you start to do something, then you see a wavelength shift, okay? You can see it here, okay? Wavelength shift, and that wavelength will stay there until you stop flowing the substance, and then it will remain at a given point, okay? In such a way that you have the baseline, you have been flowing your actual sample that has binded to your detector, and then when you stop flowing it, in some cases it will dissociate from the sensor and will go away. Not all, but some of it, and it will give you some final signal here, okay? And this is a little bit more artistic representation of how it would look altogether. Okay. Questions at this point?
Вопрос.
Yes.
Могли бы уточнить скорость работы, вот это время релаксации, за которое устанавливается стационарное положение?
Okay. Yes, it can be seconds. It can be seconds in some cases. Yes. Yes. I think I have some pictures later on with the time. Okay. Any other questions? No. Okay. So now let's go to a review of the actual biosensors and some interesting on-chip sensing architectures, okay? And finally, some real-life applications. So, this is how a complete biosensor concept would look like. A sample, a biological receptor, basically something that can capture only what you want and not all the other, okay? Biological receptor. A transducer, something that says, okay, there's something that got binded to your receptor. Okay, the transducer. So this, for instance, can be proteins, DNA, antibodies, cell receptors, whatever you can put on your surface sensor, for instance, whatever you need in this case. So just in case, just to make it bind to the other part that you want to detect. And then the sensor does not need to be optical. It can be electrochemical, like for instance the glucose sensors that we use in the diabetes, right? It is like a chemical sensor, that's electrochemical sensor, okay? And then you need, of course, to read the transduced signal and to process and monitor it, okay? But what we actually have realized, and this is a very clear case, is that we need, in some cases, in most of the cases, in more cases than in the glucose case, fast, direct, label-free, you already know what it is, high sensitivity, that means a very low limit of detection, that you already know what it is, and without having to get 1 liter of your blood, okay, with minimal substances, okay? So those are generic requirements, okay? There are many types of biosensors. The one very known for all of us are electrochemical biosensors, like the glucose biosensors. Other ones based in nanoparticles, and then, for instance, based in microelectromechanic systems, magnetic, etc. Okay? But if you make a comparison, and let me skip this one, and I'll come back later. If you make a comparison of all types of biosensors, state-of-the-art biosensors, in terms of the limit of detection, photonics ones are the winners. Okay? Integrated photonics ones based on maxillary interferometer, on a bimodal waveguide that I will present later, on young interferometer that I will not discuss, are the winners. And these biosensors are based on the concept of evanescent field. Okay? As I said, this is your waveguide, this is your waveguide. You have activated your waveguide. You can even multiplex, as you were suggesting. You can sense this thing on this area, this other thing on the other area, this other thing on the other area, etc., etc. Okay? You shine light to it, and the light feels when these have binded together, and the binding event changes the confinement of your field, because it changes the refractive index, and then that change in the refractive index, it's translated into a photonic measurement, into a photonic parameter somehow, via intensity of the light, via phase of the light, via polarization. Okay? And that can be as small as for instance, this thing. Okay? And you will see it right now. Well, this is an actual photonic chip, and this is a coin. You will see it right now. So, for photonic biosensors, there are many techniques that use evanescent field. For instance, actual waveguides, only waveguides. So you shine light through a waveguide and the evanescent field sends. Okay? Then there are ring resonators, or even disc resonators, which some of you are also familiar with. Nanopillars, photonic crystals, surface plasmon resonators, either in bulk or nanoparticle-based, nanovolt particle-based surface plasmon resonators, and interferometers. Okay, these are classical and these are nano. Okay, and as I said, I will discuss this because they have the smallest limit of detection. Okay, then they have the smallest limit of detection, and the good thing is that they are done with silicon photonics, and then we come back to integration. Photonic integration. Silicon photonics is actually the same technology in which these things are manufactured, and these things are consumer electronics. That means that they are available to the huge public, to the mass. Okay? So ideally one would like these sensors to be as well available as consumer electronics. Okay? That is why choosing silicon photonics is advantageous for making photonic integrated biosensors, because it gives you small biosensors. It can give you multiplexing, that means sensing several things on the same chip, and of course if it is tiny, it is portable, and you can use it in the point of care, in the local point of care. Okay? On young interferometer, we'll see later. If you wish, we will stop a little bit. Okay. Yes, we will stop mainly on these two, and maybe I can discuss a little bit this as well. Okay, but they are interferometers. Interferometers are the winners. Is the message here? Limit of detection. Interferometers are the winners. Okay. So. Okay, let's talk about. Okay, this one I already discussed it, which is a grating coupler, and the direction of light changes depending on what you put on top. This I'll skip it. Okay. This is a ring resonator. As I said, this is a very good biosensor. You can put light of a tunable laser, scanning laser, here, and read the output in one direction or another. I mean, add and drop, pass or drop. Okay? And if you functionalize this sensor, then via evanescent field you can sense as well, and you will see a shift of resonance as I was showing. Okay? This has a very good sensitivity, and the good thing of the ring resonator is that the sensitivity increases with what is called the quality factor. Quality factor is how narrow is this compared to the actual wavelength. Okay, the quality factor. Basically, you can understand if light is recirculating more time, which means this is very narrow, then it passes more times through the analyte, so it's actually more sensitive. Okay? This is a very good and very sensitive element, and there are many types of micro resonators, the silicon wire resonator, micro toroids, even microspheres as well. And the beauty of this is that they can be very, very small. Okay? They can be very, very small. You can have a lot of rings, one at the side of the other. Okay? That means that you can put many rings and activate each of them for a given analyte. Okay? So you have high multiplexing capability. because they are recirculating, they have very good sensitivity. You don't need to make them longer. You just need to make them better. Okay, small and better. Okay, and they can be done also in silicon photonics with a CMOS compatible process like the one used for consumer electronics. But they have two drawbacks, which are really important. Okay, you need a tunable laser to scan through the sensor, and tunable laser is not cheap. Tunable laser with the scanning electronics can be well above 10,000 euros, well above. Okay? And on the other hand, you also need an optical spectrum analyzer, either a tunable laser or power meter, or an optical spectrum analyzer. Optical spectrum analyzer is even more expensive than the tunable laser. It can be about 30,000 euros, something like that. On the other hand, tunable lasers are usually used in telecommunication wavelengths, not invisible. So actually, there is a strong absorption of other substances there, and they are hence not very useful. Okay. Despite of this, there are companies marketing sensors for the point of care using micro-ring resonators in silicon on insulator, which is this Genolite company in the United States. Okay. Then I'll skip the wires. I'll skip the slope.
What was there in between the waves? Yeah, here.
Yes?
Like not or self-fractures.
What? This?
Yes.
Oh, this is nothing. This is called tiling. This is something that is done in electronics and also in photonics. When you make complex circuits, the density of motifs, it is different in the different parts of your design. Maybe there are more waveguides here, less here. But when you etch the waveguides, the definition of the waveguides is an isotropic process. So it will etch the same rate everywhere. If the density is higher in one area than other, it will etch less here and more here. So actually, to compensate, you put dummy structures to maintain the density uniform on all the wafer. So you guarantee that the etching gives you this width here and the same width where there are more motifs, more waveguides together. So this is a technique to control the etching. Okay. This and stop. Okay. First one, Mach-Zehnder interferometer. Mach-Zehnder interferometer is a device where you put the light on one input, split it in two parts, and then collect it in the output. If nothing strange happens in the arms, I mean if the arms are equal, all the light that you put in this input will get out in the output. But if somehow you change one arm with respect to the other, then you will see a loss of light in the output. Okay? So that is a Mach-Zehnder interferometer, more or less. Is there anyone which is not familiar with interferometers? Okay? Fantastic. Then you can have, as I said, an opening here and an opening here as well. So two openings which are exactly the same. And still the Mach-Zehnder would be balanced. That means that all light going in would go out. But then you can activate or functionalize only one of them. Okay? In such a way that, I think that my colleague provided me with very good material. In such a way that your analyte binds only to one arm and not to the other. And when you flow your substances through the chip, what you're going to see is that your Mach-Zehnder response goes up and down in power. Okay? Because you are changing the phase in this arm, it goes several cycles up and down. Well, 1, 2, several cycles up and down in power. Okay? This is captured here in this equation. This is the intensity of light at the output. It is the intensity of the sensing arm plus the intensity of the reference arm plus 2 times the square root, because it is a field, electronic field interference. This is the square of the amplitude of the electronic field, and this is the phase difference between this arm that has something on top and this arm that has nothing on top. Okay? As you keep adding things on top, you keep increasing the refractive index here, you keep increasing this phase change, and this can go several times over 2 pi. That is why you see this blah 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 in your interferometer. Okay? Up and down, up and down. Okay? Is it clear? Good. Good. Then it is important to have a very clean sensors from the photonic perspective, and that means that you need to design these waveguides for 2 conditions. First of all, they need to have sufficient evanescent field for you to sense, and the Mach-Zehnder drawback is actually that it is conditioned by length. If you make it longer, it is more sensitive. You make it shorter, it is less sensitive. Okay? It is not like the ring resonator, which is recirculating. This is constrained by length. And if you make it longer, you waste more space on your wafer, so your sensor is more expensive, right? So you want to make it shorter. So you need to optimize for the evanescent field, but then you need also to optimize the structure to be single mode, because if you make it multi-mode, there will be one beam of light traveling at one speed, one beam of light traveling at other speed, and when you detect, you will detect a mixture of both, and you don't want that. You only want the mixture of one sensing mode with the other non-sensing mode, not 4 modes going over there. Okay? And this optimization also has some issues, because when you optimize for evanescent field, then when you make a term on your waveguide, everything is lost. So it's a compromise between the bends that you make here, because you need to make bends, okay, to separate these 2 parts away, the sensing and the single mode condition. So there's a trade-off there. Okay? These sensors, and you have the dimensions here, you can imagine. So basically this is 3, 4, 18, 4, 3. So basically that is 7 and another 7, 14. This is 32 millimeters if I calculate right. A bend radius of 80 millimeters, because these waveguides, as you can see, are very shallow. They are 4 microns width, but the rib is only 4 nanometers. Okay? Only 4 nanometers down. And they are designed to guide in the visible range. Okay, designed to guide in the visible range. You can see here the output of the interferometer as looked by a photodetector array and a camera. Okay, and you can see the power, barely see the power going from one point to the other, and seeing going up and down, because it's only one way guide, more intensity, less intensity, and that is what you are seeing here. As you keep flowing substances, increasing the concentration of substance on top of your sensing arm. And you can see here, for instance, refractive index variation, a linear change, and you can translate this shift to a refractive index variation because you have this equation. Okay, phase shift, and this equation, you have the length, you have the wavelength, you have 2 pi, of course. Then you have the reference arm sensing the reference arm, and then you have the phase change that you are recording here. You are recording the phase change. Every time you do one period is 2 pi, so it's easy to note the refractive index variation. Okay, so it has a sensitivity of 2 times 10 to the minus 8, 2 times 10 to the minus 8. Okay, and RIU sensitivity of it is not here in RIU, but in molar, which is another thing that I didn't explain. Okay, Young, you asked about Young interferometer. Young interferometer is this thing. It's similar to a Mach-Zehnder, but instead of ending the Mach-Zehnder, combining everything together, you just cut here, and you allow the light to shine onto a camera, and then you get interference fringes on that camera, on the different positions. It is another way of doing things. You can functionalize the different arms to sense different things, and then from the pattern you can state the relative composition that has attached to each arm. It's a little bit more complex, I would say, and there are others. Okay, but now that you know the Mach Zehnder, let's talk about the problem of multiplexing, which is something that a good question brought us very early today in the talk. Multiplexing is, I want to sense more than one thing on the same chip. In the case of the Mach Zehnder, there is only a way of doing it, which is putting more Mach Zehnders one at the side of the other. Okay? This Mach Zehnder will sense, I don't know what, A, B, C, D, B. Okay? And then you have a problem of real estate, of space. You have a problem of space. First of all, you need to feed them with light. Either you can feed them individually or together. But at the very end, this is a large circuit, okay? Because if you remember, this bending radius is 80 millimeters. So despite the picture shows them very close, it is not to scale. This is actually like something like that. Okay, so it takes a lot of space, right? So if it takes a lot of space and you need to make multiple, then you're nearly wasting your wafer space, because most of the space is not used at all. There is no waveguide in most of the space. So that is why these researchers at ICN2 that are very clever made another type of interferometer, which is only a straight waveguide. And that is the bimodal waveguide. It is only a waveguide, but it is special. How? It has two sections. One section which is single mode, another section which is higher, and it supports in the vertical direction. Okay? It's exactly the same than the Mach Zehnder. The Mach Zehnder supports two modes. You inject one mode and have one mode here and one other here. Okay? Combined. And here you have one mode, and then you feed the fundamental mode and the first order mode of this waveguide. Okay? We're going to see. Here we go. So, and here is the size. Okay? Here's the size. Again, this is a reed waveguide with a very small reed, a few nanometers. Okay? And I think I have a video of this as well. The video is self-explanatory. Okay? So basically you functionalize the top of the bimodal waveguide. This is a single mode waveguide. So, and now we have removed half of the waveguide just for you to see. And when you shine light on it with a mode, it transforms to two modes. And what you detect here is the relative intensity between the two modes. Okay? So it goes from, again, from one mode to two modes. Do it again. So there is the functionalization, there is the binding, the excitation of the single mode. So you can see the single mode here. Light, single mode, translation to two modes, and then detection. Okay? Okay. And then what you use at the end, instead of a detector, is a detector with two areas. One to detect the upper part and one to detect the lower part. Okay? And the relative intensity between the upper part and the lower part gives you an interference fringe which is actually equivalent to the Mach Zehnder interferometer, but with the beauty that you only have a straight waveguide and you can pack them close together. Okay? So as I said, the first part of the waveguide does only support one mode in vertical. Of course, in the lateral, only one mode, lateral one mode, vertical one mode, here, TE00 in this case. And then when you go there, in the lateral you only have one lobe, but in vertical you have two lobes, TE00 and TE10. Okay? And you can see exactly a very similar curve for the refractive index variation and phase change, similar to the Mach Zehnder. I think that you're going to see something moving there. So how you are flowing things onto the remodel waveguide and you see the light go up and down. Okay? So that is a camera. Okay. Let me see if I need to click somewhere. Yes, maybe. Now. So now nothing is flowing, so you see a given interference pattern. Imagine that you have a detector below and a detector on top. This is just a camera, and you can see the light going up and down. Okay? On the interference, this is the interference of the two modes, actually already captured by the camera. So if you put a detector below and a detector on top, you can say when it's going up and down, and that is the same that see in this graph here, up and down, up and down, up and down. Okay? And it has exactly the same detection limit that the Maxinder, but it is more compact. You can see the experimental setup for the lab. Let's say the translation stage are very basic because you actually have a red laser shining onto it. And then complexity here is more on the control of the flow. So you have a pump here and a flow valves here, and flow control is key here as well. Not only chemistry, but flow control. Okay, to make it sense. And as I've been repeating several times, you can activate the different sensors, bimodal sensors in this case, to sense different substances. Okay, so finally, for this part, key factor is functionalization. So there are two steps for functionalization to construct your biological receptor. First of all, introduction of functional groups to bind to the bioreceptor. And second of all, maintaining the structural and functional properties that make a stable linkage. Optimize density. If there is low coverage or there is high coverage of your sensor area, the binding will not be optimal. Okay, so it needs to be a precise density of your binding elements to achieve a good sensitivity. Okay. Also, the orientation of the sensing elements is important. Most of these things have, like these two hands on top, these proteins, binders, and they will not catch what they are aimed to catch if they are looking up, down, or to the side. Okay. So I think that we can conclude this section and make a break, and then jump into the mid-infrared thing. Okay, so some real-life applications that my colleagues shared with me. They've been in several projects, but this one was for early identification of diseases in intensive care units. You know, when you go to the hospital to get cured for something, you get three additional diseases while you are there in, and it is more likely that you die from those than from the one that got you in the hospital. And most of them are infections. And those infections, as I said before, they need to be determined in an early stage with a minimum amount of quantity and without the need of long time for culturing or harvesting your bacteria. Okay, so they have applied this B model for Escherichia coli or these other staphylococci from the ascetic fluid of pregnant women in Vallebron Hospital in Barcelona. They are also trying to avoid diagnoses that are invasive, like for instance the colonoscopy or sigma endoscopy, and for that they quantify antibodies in serum, in blood serum, which is actually of course less invasive than a colonoscopy, and they can design the chemistry to detect the specific antibodies that appear in early stages of colorectal cancer. And last but not least, they are working in several projects for pocket point of care. This is actually the size of this, so it is not pocket, right? But it is nearly pocket. You can take it to maybe in a mobile unit, in a car, and they are in this project. In fact, they are going to evaluate real samples in a field environment. So that's it for biophotonics. So I hope that I have conveyed how important point-of-care biosensors are for fast direct label-free, high sensitivity and low sample volume detection. They need to be disposable. One thing that I have not mentioned, but basically when you plug one of these photonic chip sensors and you put some substance on it, you need to throw it away, as the chemical sensors that you use for your glucose measuring. And that means that it needs to be cheap. And it needs to be cheap when it translates to photonics. It means CMOS and the small. That is why they have converted from the MZI, or converts from the MZI to the 3 molar waveguide. Functionalization is key. It does determine actually the specificity of your sensor. It determines that you're sensing this and not this, even if all the things are together. So functionalization is key. And of course there is a trade-off about sensitivity, limit of detection, and complexity of electronics. Okay, all the system around is very important, the fluidics and the electronics. In some cases, they have discussed with me, if the sensitivity is too high, even higher, they can make them more sensitive, photonically speaking, but then they have issues on the electronics, and it is not actually required in real life. So there is a trade-off on how good you make the things in photonics, how complex it gets in electronics, and how good does it need to be in real life. Okay, so there is a trade-off on all this. Okay, so that's for the biophotonics question.
I have a question about, you said us two principles of work. First of all, we can observe the shift of resonant peak, and second, we can observe the intensity changes.
Yes.
In case of absorption and fluorescent mechanics and mechanisms, maybe observe for intensity of VSD or something like that. Maybe use these ring resonators, for example, or Mark-Zander interferometers, and sense fluorescence of cells or absorbers.
Yes, that's a good question. We're starting ourselves to think about fluorescence in a way that we can, because, okay, how to tell you? Fluorescence experiments, as far as I know, and I am not an expert on that, you need to make first a measure in the background of what is called a void measure without the sample that you want to measure. So you have your background spectrum, and then you shine it onto your fluorescence, and then you capture the fluorescence. And then in capturing the fluorescence, you get the fluorescent light, but you also get part of your emission spectrum. So there is always the problem of isolating the fluorescent spectrum from the absorbed spectrum, right? And in that sense, we are thinking about photonic integrated filters, where you can have both at the same time. So actually, first of all, you don't need the initial measurement for reference, and second of all, you can isolate them spatially in two different waveguides because you have a filter, and that we are thinking about.
Probably this have advantage because they don't need any kinds of. Sometimes they don't need any kinds of
functionalization. Yes. We did a first experiment last week, so I cannot. We don't have results, but we are starting collaboration with chemistry group in the university, and we're trying to see if we can make them shine with our waveguides. There was another question there.
Показаны приборы, это прототипы или уже на производстве существует, производятся такие приборы и используются активно?
Could you make clear, Pascal, that equipment that you already shared several slides ago? Here, this one? Are they commercial available?
Я говорю вообще про все биосенсоры, которые были, есть ли налажено производство или существуют подобные прототипы, если это прототип?
Yes. Too difficult question?
No, it's too difficult to translate the formula in English. Biosensors based on photonic integrated circuit are commercial available, or is it just prototypes?
Yes, the generalized ones are commercially available. Some of the surface plasmon ones are commercially available. And these Photonics one are in pre-commercial ones, but they're going to be in the next 2 or 4 years, I would say. Okay. Any other question?
What do you think? Can we use some biosensor in a smartwatch?
But those are, I mean, this is too much advanced for a watch, I would say. Photonics depends on temperature, and you cannot have something that depends on temperature here. It takes too much power. So I think for a point of care where you can plug it or you have a battery, fine. For this, maybe no. I mean, of course you can have these tiny lasers that monitor your pulse and those things, yes, but not these interferometric things with biofunctionalization. That is not now, maybe in the future. Okay. Okay, break.